right. Well, all the results that we've got now so far, we've got reversible, Cottrell, reversible, quasi-reversible, and irreversible, have been for planar diffusion. In other words, we've assumed our electrode is an infinite plane, and our material is diffusing perpendicular to that plane surface. That's a good model for electrode, but it's certainly incomplete. There are many other types of electrodes, and very commonly used electrodes are electrodes that are spherical in shape. And as the students taking the class have already been assigned, they were assigned a problem in which they are asked to derive a Cottrell response to a spherical electrode and to see the difference. And so let me outline that. Most of you guys have already done that, so just let me outline it. And you can, if you haven't done it as part of the problem set, you might want to go through it yourself. The idea is the same as before, except we have to include some different boundary conditions in the result. What are we talking about with spherical electrodes? Remember, planar electrodes, diffusion is in a plane, or in a line perpendicular to the plane. So we call these planar, with an A, planar electrodes. Spherical diffusion, we have an electrode and the diffusion can occur radially. Of course, I'm showing a disk here, but we'd have to consider that to be a three-dimensional object. And so spherical diffusion can occur all around, radially around that sphere, from all directions, converging on that sphere location. And so this is spherical, particularly spherical for diffusion to a sphere, but we often call this kind of diffusion convergent diffusion. In other words, the molecules are converging towards some sink at which the reaction is occurring. So the boundary conditions are appropriate for what they call semi-infinite spherical diffusion. That's semi-infinite again because we've not limited the size of the source of material. The material can diffuse from an infinite distance away, so there's no walls at the end of our experiment. The materials diffuse all the way. Just like we have semi-infinite planar diffusion or semi-infinite linear diffusion, we have semi-infinite spherical diffusion. In this case, the most appropriate method of solving this equation is using spherical coordinates, and we've already actually done a spherical coordinate form of Fick's second law, and in that case, we can write it down. Concentration of O as a function of radial dimension versus time is equal to diffusion coefficient. Second derivative of that versus R plus 2 over R. I don't know why I put the parentheses there, but okay. So how to solve that? Well, for Cottrell conditions, and obviously we could go through and solve these for all the cases that we've already talked about, but for Cottrell conditions we can set up the boundary conditions as we did for the planar case. Concentration of O at the electrode surface is equal to, at time equal to 0 I should say, is equal to the bulk. For all radial direction or radial values greater than R0, where R0 is the electrode radius. Obviously, we're not talking about R values inside this electrode, only outside the electrode. Again, our semi-infinite condition, limit as R approaches infinity, is the concentration at all times is equal to the bulk. It's our semi-infinite condition. And the final boundary condition, concentration of O at the electrode surface is equal to 0 at all times greater than 0. Okay, here's again the control condition. We're not having it. The control conditions specifically state that we're stepping out into the plateau region of the wave so that the concentration of O at the electrode surface is 0. Concentration of R initially is 0 in the bulk, so we don't have to worry about that as something to worry about. Okay, the solution is easiest to approach if we make a substitution. We say substitute our variable, and let's call it a dummy variable v, and make that equal to r c rt dt. Oops. In other words, if we make this substitution of v rt equal to r c rt, then the solution becomes much simpler, as we see in a minute. So substituting in and making the form of the equations proper, first derivative of v with respect to t is equal to r dt. The derivative of rv with respect to the radial coordinate, dr is equal to c sub o rt plus r dr. And really what we're interested in is the second derivative of that. So we take the second derivative of that. Not dt, dr. All right. Again, these pens are not so great. Dividing through by r gives us a little bit easier form too, so we'll that should be dr squared up there. All right, so taking these two equations, we get this equation as we make the substitution. dv as a function of r and t, dt is equal to d0 d squared v rt over dr squared. And we can solve this, and we know how to solve that because that's exactly the same equation that we solved previously in the Cottrell case. So that substitution makes it much easier. Now, I'm not going to show you the solution. I think this is, at this point, you could probably go ahead and do it yourself. So I'll just say that once you get there, then you have to apply the appropriate boundary conditions, and then once you get a solution in the form of V, then you have to go back into the concentration form of the equation. I've actually posted a solution to that on the web as part of the solution set, and so if you get stuck, you can go ahead and look at what I've got. I think all the students basically were able to do that part. What you get when you do the solution is you get a diffusion coefficient, a diffusion current versus time is equal to a form of the equation that looks partly a lot like the Cottrell equation and part that does not look at all like the Cottrell equation. Oops. What you see is that the diffusion coefficient for a spherical electrode is equal to the diffusion coefficient that you'd get at a linear electrode, a part that's equal to the linear electrode conditions, plus a term that's constant. So this would be the normal Cottrell equation. You can see how that's derived from these two sections, and this constant part, which is derived from this section here. And so as time becomes large, the relative values of those two sections changes. At very short times, the linear part becomes an important part of the equation, and the equation for the spherical condition would be basically the same as the linear case, with some small deviation due to that constant. As time becomes very large, this term becomes very small, and so the constant part starts to dominate the system. So at the two extremes, or times very small, we get linear diffusion behavior even at a spherical electrode, and at times very long, we get a constant current at the electrode. And so writing that in this form, as t approaches infinity, we get this expression, NFAD 0 C0 star over R0. And we actually have a special name for that current. We call it the steady state current, or ISS. And steady state in this case refers to the fact that it doesn't really matter what time we're talking about, we get the same current. So as long as the time is sufficiently long so that we can consider it to be effectively infinity, and that's the important parameter, or that's the important caveat there. What is time approaching infinity for the particular system that we're talking about? But if it's long enough to be considered essentially at infinity, it really doesn't matter what the additional time is. It's always gives us the same amount of current. And so if we plot the current for a linear case and current for a spherical case, we'd get two different results. Now we'd actually have to normalize the current for the different areas, but if we do that, normalized by the area and the number of electrons and the concentration, we get a result like that. Why do we get the steady state current? Well, and why don't we get it in the planar case? Well, remember in the planar case, we've got diffusion only towards the electrode surface. And in fact, that's the only rational way that we can think about diffusion occurring. You can't think about diffusion occurring across the electrode surface because since it's infinite in all directions, it doesn't make any sense to consider diffusion laterally. There's no laterally to be concerned about. In this case, once we've electrolyzed a layer of solution near the electrode surface, more material has to diffuse in to fill that electrolyzed layer. And so what happens is that there becomes a gradient develops at the electrode surface that we can call a depletion layer. And in order to get material into that depletion layer, it starts to have to diffuse farther and farther out from solution. And because that becomes less and less efficient as time goes on, because it has to diffuse farther and farther out, that depletion layer grows and grows, and essentially the current goes to zero because it just can't keep up with the property. Now, on the other hand, and the area in which the volume in which that material is occurring in is always pretty much the same. The volume changes, but the area in which it's being fed is always the same. On the other hand, for a sphere, our sphere has a depletion layer as well, but once that depletion layer gets to a certain size, now the area has grown proportionately. So the area grows proportionally so that there's a balance takes place, so that the depletion layer occurs, but we have also a larger area in which to feed that diffusion into. So as the area grows, there's a bigger volume for the material to diffuse into, and so the process of diffusion is quite efficient for the spherical electrode. So we get a balance at some point where the amount of current that flows is equal to this term up here that's proportional to 1 over R0. We can actually derive the concentration profiles. We didn't have to do that in class for the problem set, but you can actually do the concentration profiles using the same way, same sort of equations. Concentration in the radial direction is this. Oops, R0 over R. So that's 1 minus R0 over R, air function complement. And so that's spherical. Linear, we've already derived. That would be 1 minus air function complement. Like so. So the only difference between these two concentration profiles is this term here, R0 over R, and this basically is an X term, so we can basically ignore that part of it. Let's see. And as when you can see again, when R is quite small, as the radial direction is small, this term becomes basically equal to the linear diffusion profile. For small R minus R0, basically linear and equals a hemispherical response. And you can play around with that program I showed you last time, and you can see that effect as you go to a spherical response. The gradients start to converge, and so you get, rather than gradients that drop off like so for linear diffusion, you get gradients that, although they do change with time, they tended to converge. And so that the gradient is essentially the same at the important point, and that's at R0. It's not so important about the gradient outside where the electrode is at, but the current that you're observing is the gradient at the electrode surface, concentration gradient at the electrode surface. And so what you're saying at the spherical case is that the gradient is the same at all times, and that quickly occurs. Whereas here you see the gradient changes with time, and these are curves of different time. And you can see it flattening out. And so as it flattens out, the current decays proportionately. Whereas here the gradient is always the same, and so the current is always the same. How can we tell if we're going to be in a case where we have spherical diffusion or not? Well, as I said, the point is the time, is it long enough? How long is infinite time? Well, we can sort of look at the equations and calculate those out. It turns out that if we look at a spherical case and say diffusion coefficient times time over R0 squared, if that's greater than about 32, there's 10% of that is time-dependent current. So if we look back at our equation here, when this d0t over r0 squared is greater than 32, most of the current is here, and the maximum of 10% of the current that we see is coming from this linear part of the thing. And of course, as t becomes longer, this part of this equation becomes bigger as well, and so that fraction decays even more. On the other hand, if we're interested in being in a time independent or a time-dependent case, or a linear diffusion type situation, d0t over r0 squared should be less than 3 times 10 to the minus 3, again for 10% time-independent current. Again, going back to this equation, we're just saying that when that d0t over r0 squared is much smaller than, or smaller than 3 times 10 to the minus 3, most of the current is coming from the linear part of it, and a maximum is coming from this little bit here. So a maximum of 10%. So if that's a pretty good cutoff. Usually you can measure currents much better than 10%, but 10%, 5%, and a little bit longer time. So that's a good cutoff for saying, well, okay, we're having some spherical diffusion, or we're all spherical diffusion, or I should say linear or planar diffusion or non-planar diffusion. There are a couple good examples of spherical electrodes in the literature. One of the most important ones is a dropping mercury electrode. We'll talk a little bit more about that in a minute. Dropping mercury electrodes, they just have electrode drops of mercury that are falling out of a capillary tube, and they're not quite spherical, it turns out, but they're close enough to spherical that we can consider this. The radius of a dropping mercury drop is about 0.1 millimeter. Diffusion coefficients in aqueous solutions approximately 10 to the minus 5 centimeters squared per second. So for linear behavior to be observed, we need to be t to be less than 3 seconds. So that's fairly easy to get. We can just limit our experiment to be less than 3 seconds, although in some cases where we want to be very correct, there's a correction that people will apply to avoid to get the spherical part of the situation. On the other hand, if we want to look at only spherical type diffusion, because that electrode is pretty large, we have to be at a large time that's infinite. And so here we start to get times that are more like we think about it being infinite, 30,000 seconds. And so we'd have to wait a good long time to get to spherical type diffusion under these with a drop that's even 1 millimeter in diameter. Under those conditions, we wouldn't really expect to see spherical diffusion because it would be very difficult to avoid natural convection, vibration, density gradients, temperature gradients, and so on. So effectively, we're not going to see spherical diffusion with these large drops.